Okay, so I'm going to go over a problem from Putnam, 1992 B5, which is asking me to determine if a sequence is bounded or not. And the sequence is given by a determinant, an n by n determinant, divided by n factorial. Okay, so I'm going to start with evaluating, in fact, an n minus 1 by n minus 1 determinant. So I'm going to start by evaluating some of these determinants and then see if I can see a pattern, and then I'll go from there. So if I plug in n equals 2, I get the determinant becomes basically 3, just a single number 3. So D2 is a 1 by 1 determinant, so it is just 3. So it's the determinant of a 1 by 1 matrix, which is just 3. Okay, so that is pretty straightforward. If I look at D3, and if I divide this D2 by 2 factorial, I get just 3 halves. D3 would be the determinant of 3, 1, 1, 4, and that gives me 11, 12 minus 1. And of course, from there, it becomes a bit more complicated. So 3, 1, 1, 1, 4, 1, 1, 1, 5. Okay, so evaluating determinants is not easy if you want to stick to the recursive formula, expanding along a row or expanding along a column. Typically, it's not going to be easy, but the way you want to deal with evaluating determinants is to have in the back of your mind that you have a recursive formula for evaluating determinants, but at the same time, you can do row operations. So evaluating determinants is a combination of row operations, column operations, and expanding along a row or a column, and then using recursion. And eventually, we're going to have to use induction, probably, if in fact that determinant can be evaluated. Maybe it cannot be evaluated. Maybe the formula is kind of messy, and maybe we have to just show that if you divide dn by n factorial, it becomes bounded or it becomes unbounded. So that's also a possibility. But at this point, we don't know exactly what would happen. So I'm going to take one of the rows and subtract. If you subtract, you see I have a bunch of ones that definitely gives us at least some zeros. So I'm going to take the first row and subtract it from the last row. So that becomes -2, that becomes 0, and that becomes 4. Then I'll be expanding along the last row and see what I get. So why am I expanding along the last row? Because I have a 0 in the last row. So the first term becomes -2. So you have in the first column and third row, so -1 to the power of 1 plus 3, which is 4, so that's positive. So -2, determinant of 1, 1, 4, 1. Then 0, I guess it should be -0. And then finally plus 4, determinant of 3, 1, 1, 4. Okay, so this is good because this is exactly what I had already, what I already had before. So this is in fact 4D3. So I'm not going to substitute the value here, just 4D3. And the other one is going to be plus, that's 1 minus 4, that's 3. So that's going to be plus 6. So that seems good. At least like I have a D3 here, which sounds like maybe I can use recursion and then come up with a formula, and then maybe I can prove that by induction. So that seems, I'm hopeful to see that I have a D3 there. So, but I'm going to move on and do one more example and see what I have. So D5. So that's the determinant of, so it's a 4 by 4 matrix, 3, 1, 1, 1, 1, 4, 1, 1, 1, 1, 5, 1, and 1116. Okay, so we'll do the same thing. We'll take the first row, subtract it from the last row. So 3, 1, 1, 1, 1, 4, 1, 1, 1, 1, 5, 1. And I'll subtract it from the last row to see what I get. I get -2, 0, 0, 5. Then again, I'll expand it along the last row. So I get -2, determinant of 1, 1, 1, 4, 1, 1, 1, 5, 1. So that's the first column and the fourth row. So that becomes, in fact, positive. Then, so that's minus that. So that's +0, -0, and then +5 times. So that's the fourth row, fourth column. So that should be plus. Determinant of the remaining portion. So 3, 1, 1, 1, 4, 1, 1, 1, 5. So that becomes 2 times this determinant, 4, 1, 1, 1, 5, 1, plus 5 times. So interestingly, this is also the previous term. So that's D4. Now I have a challenge in evaluating the first one, but I'm not going to evaluate the first one by just expanding it. I'm going to do something about it to reduce the computation. So what can we do about it to reduce the computation? The answer is essentially the same thing that we did before, which is let's just do row operations. So we're gonna subtract the first row. First row has a lot of ones, so I'm gonna subtract it from the other rows and see what I get. So I get determinant of, I have 1, 1, 1 here. I have 3, 0, 0. I have 0, 4, 0. And then the rest is 5d4. Okay, so 2 times. Okay, so that is interesting because now I can expand. It looks like maybe the last column would be the best one, or the last row. But this seems good because if I expand along that column, I get to a diagonal matrix here. So that's good. So expanding along that column, it's the first row, third column, so that's plus, times determinant of a diagonal matrix, plus 5d4. So this means d5 is, this guy is 2 times 3 times 4. So maybe I'll write it down as 4 factorial plus 5d4. Okay, so this is one recursion that I have. Now looking back at the previous recursion, I see that maybe this 6 is really 3 factorial. That was D4. So let me write it down here. So D4 was 3 factorial plus 4 D3. Okay, so that kind of matches what we have. And D3 was 11. So maybe D3 must have been also 2 factorial plus 3 times D2. Is that correct? So D2 is 3. So that actually seems to work also because D2 is 3. So if you plug that in here, you get 3 times 3 plus 2, which is 11. So these are what we got so far. So I'll substitute D4 into the first one to see what I get. So I get D5 equals 4 factorial plus 5 times D4, which is 3 factorial plus 4 times D3. So that gives me 4 factorial plus 5 times 3 factorial plus 5 times 4 D3. So then I'll do the same thing for D3. So I get 4 factorial plus 5 times 3 factorial plus 5 times 4 times D3, which is 2 factorial plus, so I'm substituting D3 from here, 3D2. So that gives me 4 factorial plus 5 times 3 factorial plus 5 times 4 times 2 factorial plus 5 times 4 times 3, and then D2 is 3. Okay, so it may not completely be clear what this is, but I see that this is essentially 5 factorial when 5 is missing. So that's 5 factorial over 5. This is 5 factorial when 4 is missing. This is 5 factorial when 3 is missing. Well, I can actually write this one down as 5 factorial when 2 is missing. So you can write this one down as 5 times 4 times 3 times 2 plus 1. So if you take it with 1, it's like 5 factorial when 2 is missing. And the last one is 5 factorial when 1 is missing. So this is very interesting because it looks like D5 over 5 factorial, which is what we were trying to see if it is bounded or not. It is just the harmonic series. So I'm guessing dn over n factorial is just the harmonic, just the partial sum of the harmonic series. Okay, so we can go back and look at the other ones and see that they do satisfy the same thing, which I've done before. So, okay, so perhaps we can put together all of those and in fact solve the problem. So let's see what we get. We will prove, okay, first thing I'm gonna do here before I write down the solution, I'm gonna answer the question. The question is the set this bounded? And now we determine that it actually is not bounded. We showed that it is in the harmonic series, which is not bounded. So we will show dn over n factorial is unbounded. Okay. So first is this claim. So the claim is that dn over n factorial is equal to 1 plus 1 over 2 all the way to 1 over n for all n. We will prove this by induction. D2 is equal to the determinant of 3, which is 3, which means D2 over 2 factorial is 3 halves, which is 1 plus 1 half. So that takes care of the basis step. Next, I'm gonna have to repeat what we did above, which is taking the matrix n by n matrix and then row reducing that and using induction. So dn plus 1 is equal to determinant of 3, 4, all the way to n plus 2, 1, 1, 1, everywhere here. That's equal to, so we'll take the first row and we'll subtract it from the last row. So I'll just write it down here. So it's the first row, well, it's the n plus first row minus the first row. So that basically you can do any of these, you can subtract any of these two rows, but I think that might be the best one because you can now, you can use, you can find the recursion. So we'll do that and see what we get. So if you do that, nothing is touched except for the last row. So the last row becomes -2, 0, 0, and then n plus 1. So that's what we get here. And the rest of that remains untouched. So it's 3, and then 4, and then 1, 1 here. So that's equal to. So then expand along the last row. So if you expand along the last row, the first term is going to be -1 to the 1 plus n plus 1 times -2 times determinant of the remaining portion, which is 1 all the way. So the first row is all ones. The next row is 4, 1, 1. And the last row is 1, 1 all the way to n and then 1. So everything is 1 except for that diagonal under the main diagonal. Plus, everything here is going to be 0. So I don't need to put, I don't need to write those down. This is an n by n by n by n matrix, so it would be n plus 1, n plus 1. Then determinant of 3, 4 all the way to n, and then 1 everywhere else, which is equal to -1 to the n plus 1, 2. So we'll do the row reduction again. We get 1 all the way here, 3, 0, 0, and then 4, 0 here, 0 here, 0 here. Everybody gets 0, and this one would be 0 as well, and this one would be n minus 1. Okay. The second term of that sum is exactly dn. So that's precisely dn. Okay. So, oh, I missed the n plus 1 here. Yeah. Yeah, okay. So it's n plus 1 times dn then. Okay, so we should be almost there. Now we're going to expand this along the last column to see what we get. So along the last column, we get 1 is right there. So -1 to the power of n plus 1, I'll just keep that. So that 1 is in the first row and in the nth column. So this is an n by n matrix. And then times the determinant of, when you remove that row and column, we get 3, 4 all the way to n minus 1. And then 0 everywhere else. Plus n plus 1 dn. Okay, so, and that is equal to, because that's a diagonal matrix, we get 2 times 3, 4 all the way to n minus 1. Plus n plus 1 dn. Okay. Okay, so, oh yeah, I see that I Mistakenly wrote that one as n plus 1. That should be n plus 2. So this would be n plus 1. Okay, so that makes sense now. So this becomes n. Yeah, so that becomes n. This becomes n. Okay, so that makes sense now. So now what we got is this. So dn plus 1 becomes n factorial plus n plus 1 dn. And if you divide by n plus 1 factorial, dividing by n plus 1 factorial, we get that dn plus 1 over n plus 1 factorial is equal to 1 over n plus 1 plus dn. Now, by inductive hypothesis, dn plus 1 over n plus 1 factorial becomes 1 over n plus 1 plus 1 over 1 all the way to 1 over n, which is exactly the sum of 1 over k. K equals 1 to n plus 1. Right. So that completes the proof of the claim. Therefore, since dn plus dn over n factorial is the partial sum of the harmonic series which diverges, dn over n factorial is unbounded. And that completes our proof.